Hello everyone. So we are going to have this worksheet discussed. It's from class 9 physics chapter gravitation worksheet 1. This has a total of 8 pages, a pretty big worksheet. I'm going to solve the first page today comprising 10 questions. Not everyone viewing this video may have the questions, so don't worry, I'm going to have the question displayed before I solve or discuss any question. The first 3 questions in this set are MCQs. So I've written those questions on the board. Starting question number 4, I'm going to have, as I said, I'm going to have the question displayed, and then I'll have those discussed or solved. So let's get started. So first one, the force which attracts two bodies towards each other. I think a no-brainer. I think we know this. This is all about gravitational force, right? It's the gravitational force that attracts two bodies towards each other when it comes to the universe. So any two bodies across anywhere in the universe, they attract each other with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So we're talking about a gravitational force. The next one, an object is dropped from a certain height. After 2 seconds, the velocity of the object will be. Now, this is a simple question, but it just needs us to have the keys right. Keys in the sense the keywords right. So in this case, the object is dropped. Mind you, it's not thrown, it is just dropped. That makes a difference. So in this case, it is dropped, which means we are talking about a free fall. I'm solving this question number 2 over here. So we're talking about a free fall, which means the initial velocity of the body would be 0. Dropped. So it just starts from rest. It starts from rest. And therefore the initial velocity is 0. From a certain height, we don't know what the height is, and we don't even need to know that in this question. After 2 seconds, write down everything that is given. 2 seconds, the velocity of the object will be, and we don't know what the velocity of the object. I reckon the acceleration is given. In this case, this is part of the question in the sense this is given, this information is given, 9.8 meter per second square. So let us write this down as well. G is given. This is 9.8 meter per second square. And then we are required to find the velocity. After 2 seconds, what will its velocity be? So V is equal to, we don't know. We know V is equal to U plus AT. In this case, A is acceleration due to gravity, and that gets us the answer. So this is 0. G, it's falling, so it's accelerating in the direction of the acceleration due to gravity. It's accelerating. The body is accelerating. The body is accelerating in the positive direction of the acceleration due to gravity. So G will be plus 9.8. And we are talking about time, which is 2 seconds. So in all, it comes to 19.6 meters per second. And that's the reason why A will be the answer. A will be the correct answer choice. Now the value of G. G we know is the universal gravitational constant. The value of G, I'm talking about question number 3 now. The value of G, this is something that you need to remember. This is 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. So these are the 3 questions. We'll now get on to question number 4. So here is question number 4 for you. You can have a look at the question. The earth attracts an apple. Does the apple also attract the earth? If it does, why does the earth not move towards the apple? So let's get this right. We know that the earth attracts the apple, and that's the reason why an apple would fall on the earth. If you just drop an apple, it would fall on the earth. The question is, does the apple also attract the earth? Yeah, absolutely it does. The answer is yes, it does. So I'm talking about question number 4. The answer is yes. Yes, the apple also attracts the earth. And why is it that the earth does not show attracted? Why is it that the apple falls on the earth and not the other way around? Why is it that the earth doesn't fall on the apple? Look, we know Newton's third law. What does it say? To every action there is an equal and opposite reaction. So whenever a force is exerted on a body by another body, the other body also experiences an equal and opposite force. If I hit a wall, I'm applying some force on the wall, and the wall is actually applying an equal and opposite force on me. No wonder I get hurt. How do I get hurt when I am applying force? It's because the other object is also applying equal and opposite force on me, and that's the reason why I experience that force. Now, in the case of apple and earth, look, the force exerted we know is equal to m into a. In this case, we have m into a as the force exerted by the earth on the apple is equal to m into a, and the force exerted, in this case let's take m as the capital M, because this is the mass of the earth that we are talking about. And when it comes to the apple exerting a force on the earth, it's once again m into a, but in this case the mass is the mass of the apple. So these two products, by Newton's third law, mind you, m into a is equal to minus m into a. To every action there is an equal and opposite reaction. Now, because the mass of the earth is huge, its acceleration is very small, whereas the mass of the apple is very small, so its acceleration, the acceleration caused to the apple is huge, and therefore the apple gets attracted to the earth and not the other way around. The product of these two is the same, but if this is a huge quantity, this must be a small quantity. On the other hand, if this mass is a small quantity, the acceleration must be huge. It's something like this. Let's say we have 10 into 2 is equal to 20. In this case, let's say this is the mass of the earth, so its acceleration is very small. On the other hand, if this is to be minus 4 into 5, you agree that the numeric value of this is equal to this. Therefore, if the mass of this is huge, its acceleration is very small. On the other hand, if the mass is small, or let's make it even smaller, if the mass is very small, 1, then the acceleration will have to be huge, 20, to make this product 20. In other words, A is huge compared to that of the earth, and that's the reason why we see the apple falling on the earth and not the other way around, even though the force exerted by the two on each other is equal. So question number 4, let me now give you the answer. The earth attracts an apple. Does the apple also attract the earth? The answer is yes. Does the apple also attract the earth? Yes. If it does, why does the earth not move towards the apple? That's because the acceleration caused to the earth is very small as compared to the acceleration caused to the apple. This answer will suffice. The next question: define Newton's universal law of gravitation, and why is it also called the inverse square law? Well, let us just look at this relation and everything will be clear. Whenever there are two bodies anywhere, they could be one in Hyderabad, the other in Bangalore, or one on the earth and the other on the moon, anywhere in the universe. Whenever there are two bodies, no matter how far, as I said, there is going to be a force of attraction between them, which is going to be directly proportional to the product of their masses. Directly proportional to the product of their masses. So if the mass of one body is m and the other one is small m, this is how it goes. It's directly proportional to the product of their masses, and it's inversely proportional to the square of the distance between them. This is what this law defines, that force of attraction between two bodies in the universe is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is first part of the question. The second one, why is it also called the inverse square law? It's also called the inverse square law because the force between the bodies bears an inverse relation with the square of the distance, and that's why it's called the inverse square law. Inverse square law. That's it. Question number 5 for you. Question number 6. A. Distinguish between universal gravitational constant, we know this is denoted by the letter capital G, and acceleration due to gravity, which is denoted by the letter small g. Now we know that this is a constant and it pertains to the force of attraction involving any two bodies in the universe. So it has got to do with the force of attraction when two bodies are separated by any distance in a universe. Now in this case, this is the acceleration that a body is subjected to when it is falling freely. Well, we usually connote or denote g, or let's not say connote or denote, we usually reference g as the acceleration due to gravity, and we call that value 9.8 meter per second square. But mind you, this value varies. Even on earth, this value could vary. At the poles, you might be knowing that at the poles this value is approximately 10 meter per second square. So this is acceleration. This is acceleration. In this case, this is measured in, this is the unit of g. G is a constant and it has a unit which is Newton meter square per kg square. This quantity g is measured in meters per second square. This is a constant. A universal gravitational constant is a constant. Its value doesn't vary anywhere, not just on earth but anywhere in the universe. This value remains the same, but the acceleration due to gravity, as we discussed only a while ago, the acceleration due to gravity varies. It has some value on earth and it varies even on earth. As I said, on the poles it is 10 meter per second square. Somewhere else it is approximately 9.81 meter per second square. On the moon, as we know, this value is only 1/6 of what we have on earth. On Mars, some value, some other value. On Pluto, it would be something else. So this varies, but the universal gravitational constant doesn't vary. All right, so question number 6b. Let's try to understand this question. Two objects, talking about two objects of masses m1 and m2. You can refer to the question. Two objects of masses m1 and m2 separated by a distance d in air attract each other with a force of 8 newtons. So we know, let's call the two cases. We're talking about two cases. So in the second case, the mass is changed and the distance between them, or maybe some of the attributes are changed. So we'll talk about this question in terms of cases. 6b we are talking about. So this is case A. Excuse me, and this is case B. So in case A, we are talking about the masses as m1 and m2. These are the masses of the two bodies, and the distance between them is given as d. So we are talking about two bodies of masses m1 and m2, and d is the distance between them. And then the force in this case comes to 8 newtons. Wonderful. How is the magnitude of the force changed when the masses of both the objects are reduced to half? So in this case, the mass is only 1 by 2 m1 and it's 1 by 2 m2. If there is no information given about the distance, it is implicit that the distance is still d. So now we have got to find f. So how do we go about? Look, in this case, f we know is equal to this. The force of attraction between any two bodies is given by this formula, g m1 m2 by d square. So this is equal to 8. This is already given as 8. Now can we determine this in terms of this value? Let us express this in terms of this value. So in this case, this will be given by g into m1 by 2 into m2 by 2 divided by d square. So we see that this value comes to g into m1 into m2 by d square into 1 by 2 into 1 by 2. We know that this quantity is equal to 8. So this can be written as 8 into 1 by 2 into 1 by 2. And therefore, this value comes to 2 newtons. So this force comes to 2 newtons. That's the answer. Alright, so in this case, question number 7, you may have a look at the question. How is the gravitational force of attraction between two bodies affected if the mass of both bodies is halved? So I recommend solving these questions this way. Make two cases. It gives you a clear picture of what we are doing and what we might be missing. This is very clear in terms of how we are proceeding with things. So how I recommend doing this is do two cases, case A and case B. Let me draw this partition so that we are able to appreciate the data and the values for each one case. So we are talking about the first case where we have two bodies and their masses are halved. So we are talking about the case A where the masses of the two bodies are m1 and m2. And these masses are said to have been halved. So m1 becomes m1 by 2, m2 becomes m2 by 2. There is no mention of the distance, so it's implicit. Implicit is obvious. It's obvious that the distance has not changed. So let us use this formula to calculate the force of attraction between these two bodies. So it gives us this. We have just kept this entire quantity as P. Let's call it P, and it will be obvious as to why we are calling it P. Just some constant P. This is a value which has come to P. Now in this case, when we calculate, everything else remains the same in the sense d square does not change. Hey, see, the denominator does not change because the distance between the bodies has not changed. So the force impacted by the distance, see, force is impacted by two factors, the masses and the distance. Now in this case, the distance is the distance is not impacting the force of attraction between the two. Why? Because the distance hasn't changed. So this is d square, whereas the masses have halved. So m1 becomes m1 by 2, m2 becomes m2 by 2. When you solve, you see that this quantity is P. I'm just trying to see what ratio or what fraction or what portion of P the new value comes to. So if I manipulate or organize rather this data, then I see that this quantity is P, which I got as P. And I'm now keeping the other factor here 1 by 4, which gives me a clear picture of how many times the force has increased or reduced. So as you can see, if the force in the first case was P, The force in the second case is 1 by 4 of p. In short, if the masses of both the bodies are doubled, the force of attraction becomes 1/4 of the original force. Now in the second case, the masses have not changed. So the force of attraction is again contributed by two factors. We know masses of the bodies and the distance between them. In this case, the masses of the bodies are the same, and therefore mass is not impacting the force of attraction between the bodies. So what is impacting? It's the distance. The distance has been doubled. So in this case, if we apply this formula and we call this quantity Q, then you would see that over here, I missed the square here, so this is d square, this quantity is q. So here instead of d, I put 2d the whole square, which becomes 4d square. So if you see, if I separate this quantity, which is the same as this, I'm able to make out that once again, the force of attraction has become 1 by 4 of the original quantity. So in this case, if the force of attraction was q, here the force of attraction is 1 by 4q. That's question number 7, 1 and 2, or it is A and B. Centripetal force that a planet requires to revolve around the sun. Let's look at the first part of the question first. Centripetal force. Whenever it comes to motion of this kind, rotatory motion or circular motion, we have two forces at play. The Earth revolving around the sun, or the planet revolving around the sun, this force that comes into picture to have the motion is called the centrifugal force. Centrifugal force. It tends to act away from the center. Away from the center. In this case, the center is the sun. It's tending to take this body away, and that's the reason why it's able to move. And the sun attracting, we know that the sun attracts the earth or any other planet towards it, just as the moon is attracted by the earth is attracted by the sun. Planets, Mars, Jupiter, Venus, Saturn, all of these planets, they revolve around the sun, we know, the solar system, and they are attracted towards the sun. Why don't these planets fall on the sun? It's because of the balance between the centrifugal and the centripetal force. It's like a key ring. If you are just moving a key ring around your finger, it doesn't fall as long as this is moving. But the moment you stop your finger, the key ring collapses. Just remember that. It needs this force. It needs this force of attraction, which is the centripetal force, and the movement, which is the centrifugal force, for such motions to occur. That's what this question is all about. So the question says, what is the source of centripetal force? The source of centripetal force is the attraction of the sun. The sun attracting these planets. The sun attracting these planets is the source of the centripetal force. So the answer in this case is the sun attracting the planets towards it is that source of centripetal force. And on what factors does this centripetal force, or does the centripetal force depend? The factors. We know that the force of attraction is determined by what? The product of the masses. The product of the masses, in this case, the sun and the planet in question. The planet that we are talking about is the other object. That's one factor. And the other factor is the distance between them. So how much this centripetal force is, depends on the product of the masses of the two bodies, in this case the sun and the planet, and how far they are. What is the distance between them is another factor. So that's question number 8 for you. So question number 9, it talks about acceleration due to gravity. Question number 9a, acceleration due to gravity. Now I'll just declare rather, one misconception that I have seen students come across. They usually relate acceleration due to gravity only to Earth. That's not the case. Let's have a generalized definition which does not explicitly say Earth in the definition, because acceleration of gravity exists even at other places. If you go to a moon, if you drop a ball, the ball will still fall down with an acceleration. That's the acceleration due to gravity of the moon. It will have a different value, that's another matter altogether, but it will have an acceleration due to gravity. Same with Venus. Again, there will be some acceleration due to gravity. It's not going to be 9.8 meter per second square, but there will be some value. What exactly it is what we are going to have a look at. The acceleration experienced by the freely falling bodies due to the force of attraction exerted by another body. If it is on Earth, then it's the acceleration experienced by a freely falling body towards the Earth. If it is the moon, it is the acceleration due to gravity. It is the acceleration experienced by the body falling towards the surface of the moon. If it is on Mars, it is the acceleration experienced by the body falling towards the Mars. That's it. So it's the acceleration experienced by freely falling bodies due to the force of attraction exerted by another body. That's acceleration due to gravity. Now coming to the second part of this question, this is data we have. We have the masses. We don't have the values given. It's only expressed in terms of the mass and radius of Earth. So in this case, the question says that the value of the mass, or the mass of Venus, is 1/4 times. Let me have a look at the question so that I don't write anything incorrect here. So it is 1/2. Sorry, the mass of Venus is given as 1/9 times. Sorry, the mass of Venus is given as 1/9 times that of M. So let's not introduce any variable unnecessarily. We already have M as the mass of Earth, and it's given that the mass of Venus is 1/9 times that of the Earth. So it clearly becomes 1/9 M. Good, we are good with this. And it's also given that the radius of Venus is half that of the Earth. So this is 1/r. Now, if the value of acceleration due to gravity on Earth is 9.8, what is the value of the acceleration due to gravity on Venus is the question. So this is what we are going to now find out. Now we know that the value of the acceleration on the Earth is given by this, g into m by r, where g is the universal gravitational constant. We know m is the mass of Earth, which we have taken as m, and r is the radius of the Earth, which is r. Sorry, there is an r square here. This is the formula by which we get the acceleration due to gravity, and it's given that this value is 9.8. Wonderful. Let's call this value equal to p. As I stated in one of the earlier questions, this value, instead of writing so many factors, and this particular factor is going to show in the calculation for the acceleration due to gravity in Venus as well. So let us just take this as p. It will be clear as to why I am taking this value as p. It will be clear shortly. Now on the other hand, the acceleration due to gravity on Venus will be equal to g into the mass of Venus this time, and the mass of Venus is 1/9 m, and the radius of Venus, which is 1/2 r the whole square. So this comes to g into m/9 by r square by 4. So this, if you can just organize this data, this is 9.8 meter per second square, folks. So this comes to g into m by r square into 1/9 into 4/1, mind you. Now this quantity we agreed to keep this as p. Now this is going to be the same factor in both. So because it's the same factor in both, we have just given a name p to it. Instead of writing this, expressing this in terms of so many variables, we are expressing this as p. So this comes to p into 4/9. So if 9.8 is p, then what is 9.4/9 of p? Now can we not find out the value of g? So this is equal to 4/9 of P. And what is P? P is equal to 9.8. So this comes to 4 by 9 into 9.8. Let me make this calculation. 4 8s are 32, 39.2 by 9, and that comes to 9 4s are 36, 32. So it's 4 3s are 27, 4 more or less. This is going to be the value of the acceleration due to gravity on Venus with this information that we have in the question. Now the 10th question, you can have a look. Identical packets are dropped from two airplanes, one above the equator and the other above the North Pole, both at the same height. So we are talking about the object dropped from the same height above the Earth, which means that in both the cases the objects will have to traverse or cover an equal distance. Assuming all conditions are identical, will those packets take the same time to reach the Earth, reach the surface of the Earth? So we're talking about identical packets. Now we're talking about identical packets. Identical packets. So let their masses be m. It really doesn't matter. That's another topic altogether. It doesn't matter what their masses are. If they had different masses, it wouldn't really matter which one. But anyway, here it is given that the packets are identical. So let them have equal masses m. One is dropped from the equator and the other is dropped from the pole. And the distance covered is h in both cases. So what do you think will determine the time? The time taken will be determined by the acceleration due to gravity. Now, just something that you are intuitively aware of. If you drop something on Earth, it takes a certain time to fall on the ground. If you drop an object from the same height above the surface of the moon, do you intuitively know that the body takes longer to reach the surface of the moon? Why? Because the acceleration due to gravity on moon is less. It's only 1/6 that of the Earth. So if something is dropped, it takes longer to fall on the surface on the moon as compared to the Earth. Now, the same thing is what we need to extend here. We know that the value of acceleration due to gravity is approximately 9.81 meter per second square at the equator, and it's 10 meter per second square at the pole. Now, if the acceleration due to gravity is 10 meter per second square at the pole, which is greater than this, so the acceleration due to gravity at pole is greater than the acceleration due to gravity at the equator. So with greater acceleration, the body will reach quicker. So the body or the object will take less time to reach the Earth's surface at the pole. So at the pole, the body will take lesser time to reach the Earth because at the pole, the acceleration due to gravity is larger, is greater. So this is all that we have for questions 1 to 10 from the set of 8-page worksheet that you have from school. Others, as I said, you must have been able to look at the questions at the top that I presented before explaining every answer. So in my upcoming videos, I'm going to try and explain the remaining questions from this worksheet. Thanks all for watching.